Okay, for this last example for this chapter, we want to look at the mass moment of inertia. If we look at this is an example of an antenna is shown and is constructive of identical small diameter uniform rods, each having 0.25 kilograms per meter. And we're supposed to determine the mass moment of inertia of the antenna about the given x-axis, y-axis, and z-axis. So again, we can look at this as composite shapes. It's small diameter uniform rods. It doesn't give us a diameter of them at all. It just gives us a length of each, and it gives us the mass per length type unit. If we look at this, we can look at a thin rod. So there's all these different shapes that are given up here. The first one is this thin rod shape that we can look at. There's rings and other type shapes on here. There's a sphere and other solid shapes, many different shapes that we have. And we can use these composite shapes, typically with the mass, to kind of figure this out. So this is the one that we are going to be using, though. Again, it has no diameter about it. What we do is we have some volume. It's just this area of it times the length. The axis that everything is defined about for this shape is through its center itself, which makes sense. We know if it is very small or thin rod that the moment of inertia about the x-axis, and as defined by this shape, the x-axis running through the center of the rod itself, is 0, because it is small enough that we can say that it is 0, that there is no moment of inertia. Technically, there is some, but it is very small, and we can ignore it or neglect it. Around the y, then, and the z-axis, which are perpendicular, and at the centroid of each of these rods is 1/12 the mass times the length. Okay, so this is the overall length, and 1/12 times the mass. So let's go on and take a look at that. This is the one we will use. I'm going to draw this on the next page and write this equation down for us. Okay, so here is the information from the back of your book about the mass moment of inertia for a thin rod. What we need to do next is to number our rods so we can analyze this. So this one, notice though that my x, y, and z axis are very different in here than they are for this single rod that is defined in the back of the book. We just need to know the relationship of these axes to the rod to be able to determine this problem. So let's label each one of these rods that we have. So I'm going to label this one as 1, this center rod going there. This one is 2. Then I will label this one 3, and this one 4. We are going to neglect, yes, that they run over each other and everything. This rod is all of rod 1. This minimal amount, because the diameter is so small, is so negligible, we aren't going to be subtracting that little piece of mass in there because of this rod 2 going through 1. So the first part is to find I sub x was the first one about the x-axis, right? I of x about the x-axis. In this case, this is our x-axis running through the first one. So what we want to do is add up each of these. So I'm going to have the I x1 plus any parallel axis for that one, which of course is mass times length or distance squared. That should be distance squared for 1, and then likewise each additional shape. Again, for each additional shape that we can do this. So let's look at the first one, Ix. So let's look for shape 1. What is the moment of inertia about this x-axis? We have that it is around the x-axis is equal to 0 because it's running right through it, just like in this example. So that one is 0. Hope I'm not making you sick by going in and out like that. The next one is for, around the x-axis, is for these shapes, rod 2, 3, and 4. And if you look at it, all of them are lined up the same. They're all running through the x-axis, which is perpendicular to the shaft itself. So we can use this formula here. And there's no parallel axis because they are running right through the center of it. So this one is rather simple, this one about the x-axis. So this is, I'm just going to say it's 3 times because they're all the same. 1/12 this mass, which is 0.5. If I take this 0.25 times 2 meters, right, I get a mass of 0.5 kilograms. So there's my 0.5 kilograms times the length, which is 2 meters squared. If I calculate this out, Ix is equal to 0.500 kilogram meter squared. So there it is about the x-axis. Now let's look at doing it about the y-axis. All right, so for the y-axis, IY, the y-axis being here in this case, right? So if I look at the first shape, shape 1, we see that it is perpendicular to shape 1, right? It is perpendicular, this y-axis is perpendicular to shape 1. So I will have this 1/12 mass times length squared. For shape 1, I will have 1/12 the mass, 0.5 kilograms, times the length squared is meters squared. So that is for shape 1, and it's right at that location, so there is no parallel axis for it. If I look at shape 2, here is shape 2. It too is perpendicular to it, right? So this really I could multiply times 2, right? It's the same for both of those. Next I'm going to look at shape 3 plus, what do I have? For shape 3, I'm way out here. Again, this is perpendicular to my y-axis of this particular shape, right? This is my y-axis, but I have some distance between the two of them that I kind of look at, and that's that 1 meter, right? That's the distance between the two. So let's look at that. So I have, for this one, I have 1/12 times 0.5 times 2 meters squared plus, now the parallel axis, 1 meter squared times my mass of 0.5 kilograms, right? But if I look at that amount, that is the same for rod 4, so I can multiply that also by 2. And if I calculate this, I end up with 1.67 kilogram meter squared. Last, we need to calculate the moment of inertia for the z-axis, the IZ, right? And if we look at it on here, z is running now through this axis here. If I look at 1, shape 1, it is again same 1/12 mass times length squared. We see for shape 2, and there's no parallel axis for it, we see for shape 2, it is 0, right? It's right through it. So let's write those two in first. So again, it's 1/12 the mass, 0.5, times the length, 2 squared. That's for shape 1. For shape 2, I have 0. For shape 3 and 4, again, these two are going to be very similar. 2 times, and let's look at it, right? I'm looking at an axis, again, that is in the z direction, which is also this direction. And if we do that, we see both of those, the moment of inertia is actually 0 for those. Well, that's interesting. All right, so let's put that in there. What about the parallel axis? Is there any effect due to parallel axis? Well, of course there is, because this axis is out here, right? And this is the one we want to go to. So we need to have that distance, which is 1 squared times the mass. Right? So 1 squared times the mass of 0.5 kilograms. And if we calculate this out for our I sub z, we get I sub z, our moment of inertia about the z-axis, or mass moment of inertia specifically, 7.5 kilograms per meter squared. And there we have how to do the mass moments of inertia. Okay. If you have any questions on any of this, please let me know, and we can discuss this.